We are now going to define the trigonometric functions, concentrating mainly on the sine and the cosine, and we are going to prove several basic identities that you have already learnt in high school. But this time everything will be done rigorously. So first is a definition. We define sin x to be x minus x cubed by 3 factorial plus x power 5 by 5 factorial minus plus minus plus so on. And similarly we define cos x to be 1 minus x squared by 2 factorial plus x power 4 by 4 factorial minus dot dot dot. Again the signs will change alternatingly. Okay. Now the fact that these two converge is straightforward. The fact that these series converge is straightforward. In fact, we have seen that the series for the exponential converges. You can reuse that to easily show that these two series converge, or alternatively there are several methods. I urge you to think over several proofs of the fact that these two series converge. So we immediately get some basic properties for free just from this series expansion. We immediately get cos of minus x is equal to cos x, and sine of minus x is equal to sine x minus sine x. These two we get for free just by looking at the series. We also get that d by dx of sine x is cos x, and d by dx of sine x is minus cos x. These two come just by term differentiation. So we have got certain basic properties. We also get, before I forget, sine 0 is 0, cos 0 is 1. This also we get for free. So some of the basic properties of sine and cosine can be immediately read out just by looking at the series. Now let's go for some deeper properties. First, the fact that cos squared x plus sine squared x, as we all know, is just 1. Well, how do we get this? Well, we already know that sine and cosine are differentiable and the derivatives of each other are related by the formula d by dx of sine x is cos x and d by dx of sine x is minus cos x. So differentiating this expression cos squared x plus sine squared x, which we call a function g of x, we get that g prime of x is derivative of cos x is minus sine x, so we get minus 2 sine x cos x, okay, plus derivative of sine is cosine, so you get plus 2 sine x cos x, which is 0. Okay, so we have got that g prime of x is 0. That means g prime is g is constant. G is a constant function. And what is this constant? Well, substitute x equal to 0, we get that this constant is equal to 1. So cos squared x plus sine squared x is equal to 1. Okay, so we have got even the most famous identity for essentially free. Now, how do we know that these are the definitions of the power series I wrote down? How do we know that these two must exactly be the sine and cosine function that you are familiar with from high school? Well, we know that because of the following theorem, which is very similar in spirit to the earlier theorem which we saw on the exponential function. Let f comma g be two functions such that f of 0 equal to 0, g of 0 is equal to 1, and f prime is equal to g prime is equal to f. Okay, just assume this much. So we are assuming that f and g are functions from R to R. We are also assuming that f and g are differentiable and the derivative of f is g and the derivative of g is minus f. How did I forget that? And we have f of 0 is 0 and g of 0 equal to 1. Then f of x equal to sine x and g of x is equal to cos x. Okay, so essentially there are unique functions with these properties. Therefore, the sine and cosine function that I have wrote down must agree with the familiar sine and cosine function defined in terms of triangles that you already saw in school. So how do we prove this? Well, it's similar in spirit to what we did for exponential, but slightly more involved because there are two functions involved in and they are acting in tandem. So what we do is the following. Let f1 and g1 be two other functions that satisfy f1 of 0 equal to 0, g1 of 0 equal to 1, f1 prime is g and g1 prime is minus f. F1 prime is g1 and g1 prime is minus f1. Let's assume that there are another set of functions. What we will show is f equal to f1 and g equal to g1. In particular, taking f1 and g1 to be sine and cosine, we get that there is a unique pair of functions that satisfy these properties, and that pair is given by sine x and cos x. Okay, so now what we have to do is we have to consider a slightly more tricky combination of f and g. We consider f g1 minus f1g, and we also consider f f1 plus g g1. We consider these two combinations of f and f1 g g1. Now immediately differentiating in a minute or two, you will conclude that the derivatives of both these functions fg1 minus f1g and ff1 plus gg1, the derivatives are both 0. So we must have constants such that this combination is a and this combination is b. Okay. Now what we do is we multiply the first equation by f, and we multiply the second equation by g. So, and then we subtract both equations. So what we'll essentially get is we'll get f squared g1 minus f f1g minus g f f1 minus g squared g1. Okay, we'll get this combination. This is equal to af minus bg. Fine. So now what we do is we already know that f squared, oh wait a second, I did the wrong multiplication, just a second. Yeah, these things are a bit of trial and error, so this is a part of the natural process of learning. What we'll do is we'll multiply the first equation by g and the second equation by f. So let me rewrite the equations and not butcher what is already there, which I'm going to now call star. I'm going to call this pair of equations star. Now what I'm going to do is I'm going to multiply the first by g and the second by f. So what we will get is gfg1 minus g squared f1 is equal to ag, and we will get f squared f1 plus fg(g1) is equal to fb. Now subtract these two equations. What we will get is gfg1 minus f1 into g squared plus f squared plus, not plus, minus fg(g1) is equal to ag minus fb. Whew. Okay, now let's see what happens. So we can now use the fact that g squared plus f squared is equal to 1, and the first and the third terms cancel. Okay, so we end up with f1 is equal to ag, or rather fb minus ag. Okay, now what you do is you look back at the original equations, fg1 minus f1g equal to a and ff1 plus gg1 equal to b. Again multiply by g, the first equation, and f to get this gfg1 minus g squared f1 equal to ag, and this time add these two equations now, and a bit of algebraic manipulation will give you g1 is equal to af plus bg. Okay, so we have managed to get the expressions for f1 and g1 in terms of f and g. Now this helps us a lot because we know that f1 of 0 is equal to 0 and f of 0 equal to 0 and g1 of 0 equal to 1 and g of 0 equal to 1. We know all of this. Okay. Now, setting x equal to 0 in both these equations immediately gives f equal to f1 and g equal to g1. Okay, this comes because you can determine the constants. The constant a will be 0 and the constant b will be 1. So we have shown uniqueness. We have proved uniqueness. Now, interesting fact is that if you ignore the conditions f1 of 0 equal to 0 and g1 of 0 equal to 1, this double star, this set of equations, expression for f1 and g1 in terms of f and g is still valid. In addition, if you assume that f1 of 0 equal to 0 and g1 of 0 equal to 1, we get f equal to f1, g equal to g1. Why am I making this seemingly unnecessary remark? Because using that, we can immediately prove the following properties or identities involving sine and cos. Let me list all of them and we will prove some of them. The others have already been proved or they are too easy. So number 1, which is the one we have been using repeatedly, sine squared x plus cos squared x is 1. We have already shown this. Number 2, sine of minus x is equal to minus sine x. And number 3, cos of minus x is equal to cos x. These two follow immediately from the power series. It's an interesting exercise to forget the power series expansion of sine and cos and try to prove this directly from the fact that sine and cosine are a pair of functions that satisfy the derivative of sine is cos and the derivative of cos is minus sine. But from the basic properties, you can also prove 2 and 3. Okay. 4 is the famous sine rule. Sine x plus y is sine x cos y plus cos x sine y. And number 5, cos of x plus y is equal to cos x cos y minus sine x sine y. Okay. Let me prove 4 and the proof of 5 is entirely similar. Okay. Proof of 5 is entirely similar. So proof of 4. Fix y equal to some constant c and consider the new function h of x is equal to sine of a plus x, or sorry, c plus x, sine of c plus x, or rather let me reuse notation, set f1 of x to be sine of c plus x and f2 of x, or rather g1 of x is cos of c plus x. Okay. Now observe that f1 prime is equal to g1 and g1 prime equal to minus f1. This follows immediately from the chain rule. How does this help us? Well, the unnecessary remark that I made, that this equation double star or this pair of equations double star is still valid just with the assumption that f1 prime equal to g1 and g1 prime equal to minus f1 is very useful now. Okay, it's very useful. What does this give us? Well, this gives us f1 is equal to, let me go back because my memory is not what it used to be, fb minus ag. f1 is fb minus ag and g1 is af plus bg. g1 is af plus bg. So let me just translate this pair of equations into more concrete stuff. What we actually have is sine of c plus x is equal to sine x b minus a cos x, and cos of c plus x is equal to a sin x plus b cos x. Okay. Now what we do is set x to be equal to 0. Set x to be equal to 0. What we get is sine of c is equal to minus a. Okay, minus a is sine c, and second equation gives us cos of c is equal to b. Okay, just by setting x equal to 0. Well, what does this give us? This gives us that sine of c plus x is equal to cos c sin x minus or rather plus sin c cos x. Okay, it became plus sin c because sin c is minus a, and similarly cos of c plus x is equal to minus sin c sin x plus cos c cos x, and we are done. In fact, I said I'll prove 4, but we got both 4 and 5, right? We got both for free. Excellent. So we have proved all the basic properties of sine and cosine, not all the basic properties, a good chunk of the basic properties of sine and cosine very easily and effortlessly. So the months of your life that you spent in high school studying these identities sort of seems like futile because we were able to get it in 20 minutes. Okay, so excellent. We will see more properties of sine and cosine in the next module, where we are going to now show how the graph of sine and cosine looks like. And to find out how the graph of sine and cosine looks like, we first need to meet one of the most important characters in mathematics, the number pi. This is a course on real analysis, and you have just watched the module on the trigonometric functions.